This smoke was caused by incomplete fuel combustion, which resulted in a loss of power. The exhaust smoke was actually unburned fuel and occurred because there was too little air available to effectively burn the fuel in the combustion chamber. Any internal combustion engine requires air to function, but it's actually the amount of oxygen in the air that determines the engine's efficiency. Air contains about 22% oxygen, and at sea level, it has 0.016 pounds of oxygen per cubic foot. At higher altitudes, the air is thinner, and the oxygen content decreases accordingly. At 5,000 feet, a cubic foot of air has 0.013 pounds of oxygen. And at 15,000 feet, a cubic foot of air has only 0.010 pounds of oxygen. Thus, there is a greater demand for air to supply the oxygen needed for proper combustion at high altitudes than at sea level. This oxygen is supplied to the engine during the intake stroke, when the piston moves down, lowering the pressure inside the cylinder. The pressure differential of high pressure outside the engine and low pressure inside the engine pushes air into the combustion chamber by atmospheric pressure. When the atmospheric pressure is insufficient, as at high altitudes, the only way to obtain more air is to force it into the combustion chamber. If more air is forced into the chamber, more fuel can be burned and less smoke will be released through the exhaust system. Even under normal conditions, it takes time to move air. Restrictions such as valve size, kinks in the flow pattern, and rough air-to-surface contact in the passages contribute to a reduction of the amount of air traveling into the combustion chamber. Thus, there is a lag in the fill time. This time lag only allows the combustion chamber to fill to approximately 85% capacity. This means that even under normal operating conditions, an engine is not performing at peak efficiency. Now, if we have an engine at high altitude whose efficiency has been reduced by incomplete combustion caused by the low air-to-fuel ratio, the unburned fuel will go out the exhaust system as smoke. We need then a way to make up for the loss of air, a way to compensate for altitude changes, and a way to raise the horsepower over and above that allowed by atmospheric pressure charging. What we have to do to eliminate all of these problems is to force air into the combustion chamber at such a rate that there's an adequate supply of air to meet the engine's needs. There are two basic methods of forcing air into the combustion chamber, by using a turbocharger or a supercharger. A supercharger is essentially an air blower which is mechanically driven at a rate governed by the engine's speed. The faster the engine is running, the more air is being forced into the combustion chamber. Gross engine horsepower can be raised by the use of a supercharger, but at much expense. An example would be a 220 horsepower engine, which has the capability of being raised to a 370 horsepower rating by adding a supercharger. In actuality, the supercharger will absorb about 50 horsepower, since it is driven by the engine. Thus, although the potential was 370 horsepower, the engine is now operating at only 320 horsepower. At high altitudes, such as those encountered in mountain driving, less air is forced into the combustion chamber because the air density at high altitudes is less than at sea level. Therefore, there is not enough air available to burn all the fuel. The other method of forcing air into the combustion chamber is by employing a turbocharger. The turbocharger theory is interesting. First, it uses waste energy for its source of power. Only about 1/3 of the heat of an engine goes for power production. 1/3 goes through the radiator cooling system, and the other third is expelled through the exhaust. The turbocharger provides a function much the same as the supercharger by forcing air into the engine, but it uses the engine's exhaust to drive an air compressor and does not tax usable engine horsepower. The exhaust of the engine is channeled to an impeller-type turbine wheel, which is connected by a common shaft to another impeller, which acts as a compressor wheel. The compressor wheel creates a pressure differential, which pulls air into the turbocharger and forces it into the combustion chamber. Now let's look at this in animated form. The exhaust gases are channeled to the turbine side of the turbo to turn a revolving turbine wheel, which is connected to a compressor wheel by a common shaft. The compressor draws in air and pumps it into the combustion chamber so that all of the fuel has enough air to support combustion. The volume of air pushed into the combustion chamber is regulated and determined by the design as well as the speed of the turbocharger impellers. There are three basic designs of turbochargers: the volute, the nozzle ring, and the pulse type. These types are classified according to the method used to direct the exhaust flow to the turbine wheel. The volute-type turbocharger has a single passage which channels the exhaust gases to the turbine wheel. A volute is a spiraling passageway, much like a snail shell, which has a diminishing flow area and, in this case, decreases from a large opening to a small opening. This change in area is required to maintain exhaust velocity throughout the volute. A constant, rather than increasing velocity, is maintained because gases pass continuously from the volute to the turbine wheel through an opening around the inside of the volute. The gases go through the turbine wheel blades and are funneled out the turbo's exhaust. The turbine wheel is connected to the compressor wheel by a common shaft. The compressor wheel has curved fins which catch the air and compress it by centrifugal force. The air leaves the tip of the compressor wheel blade at high velocity and low pressure. It is passed across the diffuser into the compressor volute. This combination changes the flow to low velocity and high pressure. The air is then directed to the combustion chamber. A second basic turbocharger design is the nozzle ring type, which is only slightly different from the volute type. Hot exhaust gases come from the manifolds into separate volutes, but instead of being channeled directly to the turbine wheel, they are funneled through a nozzle ring, such as this one. The area of the fins determines the force with which the exhaust gases hit the turbine wheel. The third basic turbocharger design is the pulse type. It derives its propulsion power from the minute time difference in the firing order of the engine. This pulse from the burst of combustion exhaust pushes the turbo at higher speeds and with an added power unattainable with constant pressure turbos. A turbocharger gets its oil from the engine's lubrication system. Oil is routed to a drilling in the shaft housing and used as both a lubricant and a coolant. It is forced toward both ends of the shaft. The pressure causes the oil to flow into the shaft housing, which has oil bleeder grooves which increase the volume of oil flow and improve the cooling capacity. The bearing floats in the housing, and the oil film allows shaft self-alignment and high turbo speeds. The oil drains by gravity into and out of the casing. Oil leakage is controlled by these stationary seals. Clean oil is a necessity. This heat shield prevents exhaust heat on the turbine side from transferring to the bearing housing and the compressor, thus reducing cooling problems and thermal deterioration. Exhaust heat energy is one factor of turbo speed. The speed of the turbo may reach 90,000 RPM. A temperature of 1300 degrees Fahrenheit is not uncommon, so it is apparent that turbo temperatures and speeds are high. Therefore, the turbo must be a precision piece of equipment. The turbo works most efficiently when all the fuel is being burned. When excessive fuel is forced into the combustion chamber, it is pushed into the turbo. The carbon deposits formed by the fuel burning in the turbine lower its efficiency. On the other hand, when there's an inadequate supply of fuel, exhaust energy is lessened and a loss of power results. As we mentioned earlier, the air input is determined by the exhaust energy and compressor design. Therefore, if the correct amount of air is being pushed into the engine, combustion is complete. Conversely, if there is too little air, the fuel will not burn completely and black smoke will result. If there's a large excess of air, damage can occur to the engine's seals, rings, and head gaskets because of the high pressures created in the combustion chamber. Engine design usually takes care of this problem. Therefore, a properly matched turbocharger must be used to supply the correct amount of air to the engine. One of the best features of a turbo is its ability to compensate for altitude changes. Because the air is less dense at higher altitudes, there is less air resistance on the turbine, allowing it to run faster. Thus, the compressor will build a larger pressure differential because of its increased speed. This, in turn, pulls in more air, and the balance of air to fuel is restored. As with any engine component, preventive maintenance is a necessity. And since the temperature is quite high, a cooling period is required prior to turning it off. To recap, we have to get more air into the engine than atmospheric pressure provides. By doing so, more efficient fuel combustion will occur. Smoke from unburned fuel will be eliminated, and an increase in horsepower will result. This can best be accomplished through the use of a turbocharger. It will assure the maximum supply of air needed for the fuel to burn completely, even at high altitudes. Hence, no smoke. This ability to compensate for changes in atmospheric pressure results in a more easily operating turbo. And all of this will help your engine run better under any condition.